Hey everyone, Paul here. I'm going to go through the review sheet for the third test and highlight where you can find those answers in the notes. When I'm done, I will upload both this video and the highlighted notes. Okay, so you can see on the screen I have the review sheet and I also have the notes, both of which I just downloaded from Canvas. Okay, so. Um, Going through the questions. So, first question: what are waves in the open ocean moving? Of course, waves in the open ocean are moving energy, right? They're not moving water, they're not moving sand, they're just moving energy. And that energy comes from the wind. Um, which kind of sets us up for question number two, which is what are the three things that determine the size of a wave and how do they work? And those are right here. By the way, I had to add duration of the wind to the notes. I apologize. Somehow those did not make it into the notes. So anyway, so three things. Fetch, the distance over which the wind is blowing, right? So the more fetch you have, the larger the waves are going to be. And then the speed of the wind, right? How fast is the wind blowing? And then the duration of the wind, which I had to add in. Sorry about that. I had to add in. So ideally, you want, fast wind blowing over a large distance for a long time. Take away any one of those, and the waves start getting smaller. Okay, so then we have what is wave height, wavelength, wave period, and wave basin. All of those are right here under this terminology of the waves. So wave height is the vertical distance between the trough and the crest. That's what most people think of when they think about how big is the wave, right? Is that the height of the wave. Wavelength is the horizontal distance between two crests. So crest to crest is wavelength. Wave period is the time it takes for one wavelength to pass you. That kind of depends on the size of the wavelength, but also the speed of the wave. And then wave base is the depth below which the water is no longer moving because of the wave. It equals 1/2 of the wavelength. So if the wavelength is 10 meters, wave base is 5 meters. So if you're 6 meters down, you don't know the wave is up there. It's going to go right over your head, and you're never going to know it's there. Okay, so let me see. How do waves behave at the beach as opposed to the open ocean? So in the open ocean, they're just moving energy, but at the beach, right, as the waves approach the beach, they start to feel bottom once the water is shallower than wave base, so 1/2 the wavelength. At that point, they'll start to interact with the bottom. They start kicking up sand, and they start to slow down, which lets the wave behind them catch up. So you've kind of got a kind of a wave traffic jam there at the beach, and then eventually they break against the shoreline. And from the time they start to feel bottom to the time they break, they're not just moving energy now. Now they're moving water, and now they're also moving, more importantly, sand for our purposes. And so, yeah. Okay, so there's that. And so let me see. Question number 5: what are beach drift and longshore current? Right. So these are two ways that waves move sand. Beach drift is just that wash of that wave up the beach face, moving sand. Right. Waves rarely, if ever, come in straight. They always come in at an angle, which means that as that wave breaks at an angle, it moves that sand up and then down and then up and then down, kind of in a zigzag across that beach face. That's beach drift. Longshore current is that current in about chest deep water, just a few feet of water right there at the beach, right? And you've experienced this. You go to the beach and you feel yourself being carried around here, usually but not always to the south. That's the longshore current, and they both move sand on the order, of 1 million tons of sand per year getting moved past a fixed point, and so it's a lot of sand. It really can be. Sorry. Okay. One more cough. All right, got it. Okay, so um, let's see. So there's that. Number 6: what are jetties, and then how do they affect sediment accumulation and erosion? Right. So if that sand is moving along the beach face, that means that barrier islands are moving, right? So that longshore current remove sand from the upstream side of the barrier island and then deposits it on the downstream side, and so the island is moving. The island is moving, and the inlets in between the islands are moving, and that's a problem. To fix that problem, we build jetties. Right, a jetty is just a wall of rock out into the water, perpendicular to the beach at an inlet. Okay, and what that's going to do, one more cough. What that's going to do is shut down the longshore current, and you're going to deposit sand on the upstream side of that jetty. The problem is on the downstream side of the jetty, where you're going to lose beach. Right, so don't do anything on the downstream side of that jetty too close to the beach. Just count on losing some beach on that downstream side. And so yeah. Okay, so there's that. Let's see what else have we got here. Jetties. Okay, kind of separate from longshore current is beach erosion, right? Which is the movement of the beach inland. Okay, this is happening for two reasons, right? And here they are right here. Sorry, I have a pagination problem there, but oh well. Oh well. Anyway, so two reasons. First of all, sea levels rising, right? The world's oceans are, getting deeper. Okay, for two reasons. One, ice is melting, but also as we warm the oceans, they actually expand. Everything expands when it gets warm and contracts when it gets cold. Everything does. And water is no exception. So as you heat the water, that water expands. So as we heat the planet, that water expands. And so, yeah. The second thing, though, so sea level's rising, but also once sea level rises, now it needs to come back into equilibrium with the shoreline. And this gets down to that equilibrium slope that we talked about, right? You raise sea level, and then the shoreline is too steep, so the beach has to chew its way inland, right? So people have a bad habit of going, well, if we're expecting 20 feet of sea level rise and my house is 30 feet above sea level, I'm going to be fine. Maybe not, right? Because that beach is going to chew its way underneath your house, right? And when you think about, these very dramatic pictures you see of beach erosion, the problem is not that the house is getting flooded. The problem is that the house is, getting undermined, right? That the water's going underneath the house, not into it. And so, yeah, so what do we do? Well, one of the first things we do is hard stabilization, right? So hard stabilization is, pouring some concrete, right? Make a seawall, make a groin, make a breakwater, something like that, right? Pour some concrete, pile some rock up, something like that. Okay, that's what we mean by hard stabilization. And so there's three different kinds, and that's question number 9, right? And here they are right here underneath, oddly enough, hard stabilization, right? Seawalls, groins, and breakwaters, right? Seawalls are, walls meant to protect property. They do an okay job of protecting what's behind them. Not great, but okay. But the beach in front of them is just going to go away. You don't have seawalls and beaches. So those two things just don't go together. The minute that wave energy touches that wall, that beach is gone. Okay, and so yeah, groins are like jetties. Only jetties are at inlets. Groins are just on a beach, right? So a groin is just rock going out into the water perpendicular to the beach. It behaves like a jetty, right? It's going to accumulate sand on the upstream side. The problem is, of course, on the downstream side, where you get erosion issues. Breakwaters, where groins are walls going out into the water perpendicular to the beach. Breakwaters are parallel to the beach, right? There's some of these at Honeymoon Island, parallel to the beach. And so what's going to happen there is you're going to shut down the wave energy. Sand is going to build out to the breakwater. And that's fine there, but one more time, if you're trapping sand somewhere, you're starving it somewhere else. So go look downstream and make sure you're not having erosion problems downstream, right? That's just like the whole thing with beaches is if I trap sand in one place, I starve it in another. Okay, so alternatives to hard stabilization, we talked about two things: beach renourishment, and then we also talked about soft stabilization. Oops, I don't have no idea what I did there. Let's just undo it. There we go. And highlight. There we are. So yeah. So renourishment is just the idea that, look, if you don't have enough sand, add sand. right? Build a beach by pumping sand onto it. This isn't as easy as it looks, right? It's tricky to get it right. You have to match the sand, you have to match the equilibrium slope as much as you can. You can never exactly match the equilibrium slope, so it's always temporary. The beach is always going to chew through your renourishment project. It's just a matter of how quickly is it going to chew through your renourishment project. The other thing is it's expensive. It's like $1 million a mile, y'all. It is not cheap to do. And so, yeah, we do it. We do it all the time because you get to a point where you just don't have any choice. But it's harder, and it's getting even harder because there is actually a global sand shortage right now. And so it's harder and harder to do this. Another alternative is what's called soft stabilization, and this is just make using shells and driftwood and things like that to kind of armor your beach. Plant sea oats, plant seagrass, plant sea grape, all those plants that grow on the beach naturally, and you'll put those in to help hold that sand. Soft stabilization works great. If your beach is more or less okay to start with, right? Soft stabilization is a way to maintain a beach. It will not restore a beach, but it will maintain one. And so yeah, so I believe yes, there is the beach stuff. Cool. Let's move on to climate change then. So let's talk about climate change. So here are the notes here. And so first of all, how is the air around the Earth heated, right? And by this, what I want you to get is this, right? So here's the thing, and I say this over and over again, right? The sun doesn't heat the air. The sun heats the earth and the earth heats the air. That's the way that works. Okay. So short wavelength radiation light comes in, it reaches the earth. Okay. And the earth absorbs it, re-emits it as heat. Okay. And then greenhouse gases trap that heat. That's the way that works. The sun doesn't directly heat the air. Our weather happens from the ground up. Okay. So oddly enough, what I have down there underneath there, right? When you add more heat trapping gas to the air gets warmer. Crazy, I know, but there it is. Okay, so alrighty. So what is the carbon cycle? How does the carbon cycle work? So the carbon cycle is just the idea that under natural conditions, you're going to be moving a lot of carbon dioxide around the earth, right? Trees put carbon dioxide into the air, but trees also take carbon dioxide out of the air. The oceans add and remove carbon dioxide to and from the air. Soil microbial decomposition releases carbon dioxide into the air. There's a lot of carbon just being moved around. So when people say, well, but trees are putting more carbon into the air than we are, and that is true, but trees are also sucking out every bit of that carbon and then some. Right? So I just want you to understand that, yeah, carbon gets moved around naturally all the time, right? The problem is, as we burn fossil fuels, right, that carbon dioxide that we add can't be absorbed. Some of it can, but not all of it, and it accumulates, right? And so, yeah. So let me see. Carbon cycle. How does the current rate of climate change compare to the natural rate of change? It is much, much faster, right? The Earth's climate noodles around a little bit. It goes up, it goes down, right? Not the way it has since the Industrial Revolution, though. Since the Industrial Revolution, the levels of warming have been way, way faster than what we would consider to be quote unquote natural, right? Because we're forcing it. Because we're adding carbon dioxide to the air. We're putting 100 million tons of carbon dioxide into the air every single day. And that heat trapping gas is oddly enough trapping heat. Okay, so I'm trying not to be that old man on the porch shaking my fist as I do the review here. Okay, so what are some of the feedbacks, right? So there are a few things that are going on here that make the problem even worse, right? And one of them is what we call albedo or ice, right? So let me explain that word. Albedo is the percentage of incoming sunlight that is reflected, okay? And ice reflects sunlight, okay? This is how ice keeps the planet cool. Ice doesn't keep the planet cool because it's cold. It keeps the planet cool because it's light in color, and so it reflects sunlight, right? So, as we warm the planet, Ice melts. That means we're reflecting less sunlight. That warms the planet. Ice melts, and we're reflecting more sunlight. You can see how we're in a loop, right? That's what I mean by a feedback. Okay, so that's important. Water vapor is important, right? As we warm the planet, we evaporate more water. Water vapor is a very powerful greenhouse gas. And so, as you warm the planet, you evaporate more water, which warms the planet, which evaporates more water. And you can see once more how we're in that loop. Methane is the same way. There's a lot of methane trapped in sediments, there's a lot of methane trapped in permafrost. And so, as we warm the planet, we release that methane. Methane's a greenhouse gas that warms the planet even more. We release more methane, and you can see one more time we're in that loop. That's what I mean by a positive feedback. Okay, and so yeah, so there they are. I mean, I don't need you to go really, really, really deep into them, but you know what they are. You just kind of know what they do. Okay, so consequences of sea level rise of global climate change. And so here they are, right? And so yeah. So first of all, we already talked about beach erosion and sea level rise, right? As we um, as we melt ice. Now, not sea ice, but as we melt glaciers, okay, those glaciers run into the ocean. That makes the ocean deeper. As you heat the water expands. That makes the ocean lap up on shore, right? And so, yeah. So, sea level rise. Also, more weather related disasters, right? We're getting more hurricanes. We're getting more flooding. We're getting more storms. We're getting more fires. We're getting more everything. We're not getting more earthquakes, right? Climate change doesn't affect earthquakes, okay? But other stuff, other climate related stuff, absolutely, absolutely. We have stronger, wetter hurricanes that are reaching further inland. Places like Central Texas and Western North Carolina are suddenly having to deal with hurricane flooding, and they're just not set up for that. They're really just not set up for that. So yeah, I mean, we're also having more issues growing food, which should maybe make you think a little bit. That's really not good. Okay, so when we think about responding to climate change, we tend to categorize things as prevention, mitigation, and adaptation. So how do those work? And that's the last question. That's number 16. Okay, um, so here we go, right? And so here it is, right here. Prevention, and there's a bit here, but I'm not going to go really, really deep into this. So don't freak out or anything on me. And there we go. Okay, so prevention is keeping climate change from happening, and it's too late for that. It's here. So there's that. That's easy. Mitigation is saying, okay, it's here, but we need to reverse it, right? We need to make it not so bad, and we need to reverse it. And so how do you do that? Well, there's tricky, dangerous things. Put sulfur dioxide into the air. Try to increase oceanic photosynthesis. Weird things like that. Um, Carbon capture, like suck the carbon dioxide out of the air, not a bad thing, but no one's sure you can do enough of it, right? It's just bad, right? Obvious things, use less fossil fuel. This is why we want to do renewable energy, right? This is why we want to do wind and solar and nuclear and any other alternative energy you can do, hydroelectric, geothermal, tides, waves, I don't know, anything other than burning a fossil fuel, other than burning coal or burning petroleum. Don't do that. Um, Less obvious things: planting trees. Planting trees, there is no downside to trees, but you're not going to plant tree your way out of this. You're just not. You can't. There's not enough room to plant enough trees. There's just really not. Oddly enough, painting things white helps. Um, Especially roofs. Now, don't go paint your roof white. There's things, but generally, the urban heat island is a real thing. Cities are warmer than the country is because there's so much black asphalt. And then eat less beef. Crazy, I know, but eat less beef. Cows make methane out of both ends. Fewer cows means less global climate change. It just that's just true. And so yeah, beef is very energy intensive. It's also very water intensive. You burn a lot of fossil fuels raising and processing and transporting or whatever a cow. You just do, and that as I said in class, that hurts my soul because the only thing I love more than a hamburger is a steak. But no, eat chicken, okay, or eat more chicken. You don't need to like purge it, but eat less. Okay, so and then adaptation, right? Adaptation is something we need to get better at, and I said this in class. We need to get better at this, right? Adaptation is living with it. living with it in an intelligent way, right? We need to manage forests better for fires. We need to really think about whether or not we want to be living in flood prone areas inland. You know, yeah, we really just do, right? We need to think about whether or not we want to be keep living on beaches with the water rising the way it is. We need to be breeding heat resistant crops. Agricultural zones are trying to shift northward, but they can't. It's a problem. We need better energy infrastructure, right? We need, one of the reasons we're having, sorry, that's not a reason. One thing that's happening is we're having trouble bringing a lot of this renewable energy online because our energy grid just isn't built for it. And so we need to be able to bring all this renewable energy online. When you think about air conditioning in northern areas, right? There are places where you used to not need air conditioning where now you do. Um, the weather phenomenon that kills more people than anything is heat. And in the lecture, I showed you a graph and I showed you a map. And so, yeah, um, we also need to think about food aid, right, to southern areas where they're suddenly not able to grow enough food. Starving people do bad, stupid things, and we don't need to be dealing with that. We really just don't. Okay, so I tried to end on a little bit of a hopeful note. I think I might have failed at that, but that's okay. Alrighty, so there it is. Okay, I just wrote the test. The test is 20 questions long, y'all. 20 questions. That's a little bit concerning for me because the more questions you have, the less each question is worth. With 20 questions, each question is worth 5 points. That means that if you miss two, you're at a 90. If you miss three, you're at a B. You're at an 85. So, but I'm hoping there's a little enough material here that y'all can hammer on this test, and it'll be good. So anyway, okay, I'm going to save this highlighted version of these notes. I'm going to save this video. I'm going to upload both of them so you have them. Okay, all right, y'all take care. Get with me if you have any questions or issues or anything. All right, bye bye.